Morning, guys. This is, well, I guess you could be watching this in the afternoon. I'm doing this in the morning. This is section 4.2. So I want to go through the notes with you, which again I'll have posted and hopefully will help you with the homework this week. So what we're going to do first is just review a little bit from section 4.1, looking at those exponents again. So we're going to be doing more with integer exponents in this section, trying to do some essentially math with those exponential terms, okay, multiplying, dividing, things like that. So remember that an exponential term here is just a multiplied times itself several times. Get that the right size there so it all fits. So just a times itself however many times that exponent tells us, right? So this is a times itself n times. All right, where a, remember from 4.1, we call that the base, and n is the exponent. The two other things we want to remember are that zero exponents, anything to the zero power is 1. That one kind of is the least intuitive I see through teaching this. We want to say that anything to the zero power is 0, but it turns out it is 1. And then any negative exponent doesn't mean the number is negative. It means we have 1 over a times itself that many times. So we're actually dividing instead of multiplying by a in the case of a negative exponent. We're going to see all those things again today. And what we're going to start doing is looking at, okay, what if I have these exponential terms multiplied together? To start off with, what if I have the product of them? Is there some way I can simplify these expressions below? So we're going to end up with a rule that's going to help us simplify this. So of course there is a way to simplify some of these that we see, but in order to understand where this rule comes from, I just kind of want to write out what we know so far. So what we know so far is that 7 cubed means I have 7 times itself 3 times, and then 7 squared is 7 times itself twice. So here is 7 cubed, and here is 7 squared being multiplied together. And we'll see, since that base is consistent all the way through, that this is actually just 7 times itself 5 different times. So 7 cubed times 7 squared becomes 7 to the 5th, and we can simplify that expression to just be one exponential term. So can you see what's happening there? We took 3 7s and 2 7s to become an exponent of 5. So we are adding those exponents together. So that's the rule we're going to see. So if we have bigger exponents that we don't want to write out, we can just say, oh, 3 to the 6th times 3 to the 10th, that is 3 times itself 6 plus 10 more times, that is 3 to the 16th power. One really important note here, though, is that we cannot do this with different bases. And here's the reason. Write this expression out. 2 to the 4th times 3 squared. This is not 6 to the 8th or 6 to the 6th or something like that, okay? Because when we have 2 to the 4th, that's 2 times itself 4 different times. And when we have 3 squared, that's 3 times itself twice. There's no way to write this all in terms of one base. We would actually just have to multiply all those numbers together to figure out what this number is. So there's no simplified exponential term. This is just 2 to the 4th times 3 squared. But we can do that simplification when we have the same base that we're looking at on those two exponential terms. That makes a rule for us where if we have the same base, so I'm just going to use a common variable a, and let's say I have a to the n power, and I multiply, we're doing products here, that by the same base to any other power, and it turns out that those powers, right, can just be added like we realized up here with the first two examples. So this becomes a to the n plus m. And we have the product rule. Now, I won't necessarily need you to remember those exact rules, but you will, the names of those rules, but you do need to remember that, oh, when I'm multiplying two exponential terms together, I need to add those exponents, okay? So this is the meat of what you want to remember. Now, there's about 6 rules we're going to look at today. And we want to, again, just understand where they're coming from. So the next one is going to look at, okay, if I can multiply and simplify some exponential terms, can I do some quotients or division and simplify these? And it will turn out that we can. So this first one you see here is 7 cubed divided by 7 squared. So again, to understand what's going to happen with this rule, let's just write this out fully as the exponent without the exponents. So 7 cubed is 7 times 7 times 7, and 7 squared is 7 times 7. Now what happens here, right, is anytime we're multiplying everything, if I have 7 divided by 7, that is just 1. So this 7 can cancel with this 7 because it becomes 1. And this 7 can cancel with this 7 because it becomes 1. So in the end, my final answer is just 7. Now, if I'm looking for what rule just happened, think about that. 7 by itself is the same thing as 7 to the first power. So we took the 3 7s on the top and subtracted the 2 7s from the bottom to become 7 to the first. So if we follow that same rule to simplify this next expression, notice it's very important that we took 3 minus 2, right? The 3 on the top minus the 2 on the bottom. You'll notice, though, that with this next example, if I follow that same pattern, I'll get 3 to the 6th minus 10. And 6 minus 10 is a negative number. That's 3 to the negative 4. And that's maybe the first time we see why we have that negative exponents mean we're dividing. Because what happened here is that we had more 3s left on the bottom than on the top. In fact, there were 4 more 3s on the bottom than the top. So that's the same thing as 1 over 3 to the 4th, leaving those 4 3s in the denominator. And we will want to finish out exponential expressions with the positive powers. So 1 over 3 to the 4th is our final answer. But we can still do that subtraction and realize that a negative number just means that those bases should have been divided by or left in the denominator of our fraction. All right, so last one here, we're like, okay, we've got a good rule going, but can I just take 4 minus 2 here and make that the power of 2/3? And of course we cannot, because thinking again about what this means, that's 2 times 2 times 2 times 2 over 3 times 3. We're in no way getting 2/3 here. The only way, again, to simplify this would be to actually solve those exponents. So if we're leaving this as an exponential term, the most we can do is just leave it alone as 2 to the 4th and 3 squared. All right, so our quotient rule now then is, okay, if I have the same base again, if I have something, let me make sure I have enough room here. If I have something like a to 1 power over the same base to any other power, then so long as I always take the numerator power minus the denominator power, I can simplify those quotients of exponential terms pretty easily. And I see another rule I can use to simplify exponential expressions. Let's see what we can do when we have a power to another power. So this is 5 cubed squared. So in order to figure this out, let's write it out. If I have 5 cubed squared, let's deal with the outside exponent first. That means I need to multiply whatever's on the inside of this parenthesis times itself twice. So that would be 5 cubed times 5 cubed. Now, what I'm looking at is a product, and I can apply the product rule we just learned. That's 5 to the 3 plus 3, and that is 5 to the 6th power. So notice now with that original problem, what did we do with 3 and 2? What did we do with those 2 powers to get to the 6th power? We multiplied 3 times 2 to get there. Okay, so let's try it again with this one. 7 to the 4th to the 5th power would be that base, which is now 7 to the 4th, times itself 5 times. And then we have the product rule just over and over again. This is the same thing as 7 to the 4 plus 4. Notice I'm going to have to add 4 however many times that outside exponent tells me to. And that repeated addition is just multiplication. That's 7 to the 4 5 times. And we can simplify that to be 7 to the 20th. So our power to a power rule, when I have two exponents without another base with this outside exponent, power to power, I have that one base to one power and then to another power. And if I have that, then what I need to do, what we see here, is that ends up in a multiplication of powers to simplify those two powers into just one power. All right, so let's keep going. We're about halfway there. That's half of our rules. Okay, the next ones are going to be all pretty similar. So we can only do these types of things, you can notice, because exponents are multiplication. There's no way we can simplify addition or subtraction of exponential terms. So what we're going to do now is just try and put some more of these rules together. So what if we had a product to a power? All right, what will happen in this case? So let's write this first one out again. So this base of 7 times 3, so try not to actually go ahead and multiply those. We want to leave them as separate bases and see what happens. So if I leave those as separate bases and I square it, then I end up with 7 times 3 is my base, and it needs to get multiplied times itself twice. So that is just 7 times 7 times 3 times 3, if I reorder that multiplication, which we know we can do. So what happens here is I end up with, 7 gets squared times 3 squared. So both of those bases in the product get the exponent on the outside to become 7 squared, 3 squared. Now we could simplify those numbers, but again, we're just trying to figure out what that rule is overall. So we see there that the rule is that exponent goes to both. But now what happens if the inside terms already have exponents? If you can see that right now, it's a little bit confusing because we've got a product and a power. So do we apply the product rule? And for this 3 to go to 4 squared, do we take 2 times 3 or do we add? So let's write it out again. My base is 4 squared times 5 to the 4th, and that needs to get multiplied times itself 3 times. So that's what we're looking at when we expand that cube out. And then if we think about combining 4 squared times 4 squared times 4 squared, we can see that we have 2 4s, 4 4s, and 6 4s being multiplied together. So we end up with 4 to the 6th. And so that power to power rule does apply to both. We also end up with 5 to the 4th, that's 8 5s, that's 12 5s. So times 5 to the 12th. Okay, so if you have a product to a power, the power rule, the power to power rule gets applied to both. Okay, so we have a to the n. If we have one base to a power, another base, so now this second base is not going to be the same, to another power, and we take that all to yet another power, then all we need to realize here is to simplify this expression, to get rid of those parentheses and simplify that outside power, we need to multiply the powers and essentially distribute that outside power to both. So this is a to the n times r times b to the m times r. All right, so we can simplify that outside power and make this down to just those two bases to one individual power using that product to power rule. So you might think, okay, can I do that with division too? So let's find out. Taking those same bases but dividing them instead, write it out. 7 over 3 squared would be 7 over 3, take that base times itself twice, to expand the outside power. And you'll see there, yep, that's 7 times 7. Remember to multiply fractions, we just multiply across the top and bottom. So this becomes 7 squared over 3 squared, and we do see that the squared just goes to both of the bases in the quotient. Here, we'll see again, are we going to take the 2 plus the 3 or the 2 times the 3 to simplify those powers? Okay, let's write it out to make sure. We can pretty much guess from the first one, right? The idea from multiplication is that it should be multiplied, that we should apply the power to power rule to both. But let's write it out to make sure. So 4 squared over 5 to the 4th times 4 squared over 5 to the 4th, 3 times to expand that outside power. And remember, when you take 4 squared times 4 squared times 4 squared to multiply these fractions, that's a total of 6 4s being multiplied together over a total of 12 5s being multiplied together. So again, we just apply the power to power rule to both if we have a quotient to a power rule. So if I have a to the n over b to the m, 2 different bases, all to another power, then I have that I can just simplify this by taking the top power times the outside power and the bottom power times the outside power. Okay, now this next one is actually very similar, and we could essentially apply the same rule, but there's one nice trick that can happen anytime you're working with negative exponents on the outside of fractions. There's a lot of stuff going on here, right? So you could think about, okay, according to my last rule, that means that each term of this quotient gets the power, but it's a negative power, and that's okay, the rule still applies. So if I apply the last rule here, I end up with 7 to the negative 2 over 3 to the negative 2. But then what happens is, because you're distributing that outside negative exponent to everything, you end up with a ton of negative exponents you have to simplify. Now, what does this mean? So I do kind of want to write out each one of these steps so you can understand what happens here. So remember, to make a negative exponent positive, it means we're dividing by it. So if I think about what happens in this fraction, on the top I really have 1 divided by 7 squared. And on the bottom, I really have 1 divided by 3 squared if I make those powers positive. Now that's a complex fraction, and we don't want to leave our answer like that, even though it is positive exponents. We want to simplify this. So think about what this means. This is 1 over 7 squared, which needs to be divided by 1 over 3 squared. And anytime you divide by a fraction, it's the same thing as multiplying by the reciprocal. So this is 1 over 7 squared times 3 squared over 1. And you'll see what happens with that original equation is that the 2 can just flip. This becomes 3 squared over 7 squared. So a negative exponent will just flip that fraction. We started with 7 to the negative 2 over 3 to the negative 2. And now we have 3 squared over 7 squared. So what you're learning here is that if I have a negative exponent in my denominator, I can make it positive by moving it to the numerator. If I have a negative exponent in my numerator, I can make it positive by moving it to the denominator. Now, one little bit simpler way than now just realizing that that happens is that if we go to the next one, I'll show you what this rule kind of really hones in on, is that I can take care of that negative exponent on the outside from the beginning by just saying, oh, it's going to flip that fraction. Everything on the bottom is going to move to the top. Everything on the top is going to move to the bottom, and go ahead and do that flip before I distribute the exponent. So I'm going to move 5 to the 4th to the numerator and 4 squared to the denominator. And then that makes this power, once the fraction is flipped, the power is now positive. So now I can just do the quotient to power rule and realize, okay, both of these powers get multiplied. So that's 5 to the 12th over 4 to the 6th. Okay, so if we have a quotient to a negative power, it is helpful to say, okay, if I have that one base to a power over another base to a different power, and I have a negative power on the outside, I can just flip the inside, flip that fraction, and that power will become positive when the fraction is flipped. And that's a helpful rule to do, to just get rid of that negative from the beginning. We don't like working with negative numbers. It causes a lot of errors because we lose the sign along the way. So just make it positive from the beginning. All right, so we're going to sum up all those rules. There's 6 of them in total. The first one we had was the product rule, where if we had the same base times itself with different powers, then test yourself. What do we do to the powers? Add them. And if we have the same base to different powers divided, what do we do to the powers? We subtract them. And if we have the same base to one power and then raised to yet another power, what do we do to the powers? We multiply them. And then we kind of started combining all of these rules. So we said, okay, what if we have a product of actually 2 different bases to a power? And that meant we could distribute the power applying the power to power rule. So this meant I need to take the first power times the outside power and the second power times the outside power. Same thing if I instead see a quotient to a power. I need to take each power times applying the power to power rule, the outside power, and that should be a B on the bottom there. Oh, I don't know why it's doing that. Okay. Apparently I just recorded something for some reason. Okay, just get rid of this. Okay, so we distribute that quotient rule there. Okay, and then finally, if we instead, almost the same thing, but a very helpful rule, if we have that negative exponent on the outside, just the one we see right above there, and we can flip the fraction on the inside and make that power positive to then apply rule number 5. All right, so what we don't want to do is write out all the things, right, that we were doing in order to learn these rules. Now we just want to take these rules and simplify more complicated exponential expressions. So we're going to practice some more simple ones at the beginning here, and then we're pretty quickly going to get into some ones that are going to be a little bit harder. Okay, so try these maybe first, and then so pause the video, practice this. It's normally what I would have you do in class, and then we would go over it. So see if you can practice this and then check the video and see if you got it. All right. On the first one here, we have a product rule. So you should be taking 8 to the 6th plus 34. And here you should have gotten 8 then to the 40th power. Now, anytime that you have some number that's so big, just go ahead and leave that exponential term with the big power. We want to use those exponents to summarize really big numbers. Now, if it's something like 8 squared or 8 cubed, you can go ahead and simplify that. Okay, here on this next one, you should have taken 10 to the 34th minus 12 since we're dividing, and gotten 10 to the 22nd, which again, I would just leave as 10 to the 22nd. On this next one, you might have missed this. You want to be careful. The -3 also gets cubed. So the -3 is one of the bases. It gets cubed and x squared gets cubed. So it's helpful to maybe write out that middle step where you write out what base, each base individually that is being, that is getting that outside exponent. So in the end, we have a negative number that's cubed, so that'll stay negative. That's -3 times -3 times -3. You can use your caret key in your calculator to do that, but always make sure you remember the parentheses. You should have gotten in that. We can simplify, right? That's -27. It's a small number. We can go ahead and simplify that. X to the 6th. Remember, you will multiply when you have a power to power going on. All right. In this next one, we have a lot of different bases that need to get cubed. Now you can do that from the beginning, or one thing you might notice is that we can simplify this fraction on the inside first. 2 and 4 can be divided. So I like to do that first. Anytime I have a fraction that maybe has something where I can simplify, I will go ahead and do that. So on this one, I would say, okay, well, 2 over 4 becomes 1 over 2, and the x and y are still there. And you wouldn't even have to write that 1. You could just write negative x here, because negative 1 times x is just negative x. And then you can cube each thing. So negative x will be cubed, 2 will be cubed, and y will be cubed. Now if I cube a negative, it still stays negative, so this whole thing becomes negative x cubed over 3 cubed is 8 y cubed. Okay, so you can simplify on the inside first, or if you didn't simplify on the inside first, you'll see you'll get the same answer either way. This next one really focuses in on the fact that we do not have to change negative exponents from the beginning. So if you see this, you can just straight apply the product rule. This is x to the negative 2. It's the product rule, so we would add the exponents, and that's fine. Negative 2 plus 4 would show those two x's being in the denominator, and we'll end up canceling them and saying, oh, 4 minus 2 is 2, and this just simplifies to x squared. You can still apply those rules even if you see negative exponents. Moving on to number 6 and 7, this is that big difference where it's really important you're using parentheses in your calculator whenever you have negatives to calculate these. This is negative 5 times 5. Because that negative is not in parentheses, it is not squared. So the answer to this one is negative 25. Very different to the answer to number 7, where the negative is in parentheses. This is negative 5 times negative 5, and that becomes a positive 25. And you'll notice you have to put those parentheses in your calculator to get that correct answer. This next one has that negative exponent on the outside. So you could again think about this one as doing, okay, that's 3 to the negative 3, that's y to the negative 3, that's z squared to the negative 3, and then dealing with all those negative exponents separately. Or I would say, well, if everything is to the negative power, then this is the same thing as 1 over, send everything to the denominator. 3yz squared all to now the positive 3 power. And then just distribute that positive 3 power. So you don't see a bunch of negative exponents and get confused. So this would be 1 over 3 cubed, y gets cubed, and again z squared gets cubed. So just make sure there that when you simplify z squared cubed correctly. That's power to power. So again, 3 cubed, is 27. Y cubed is simplified, and this would be z to the 6th, not z to the 5th. It's power to power, and you need to multiply those two powers. So this would be your final answer here. Another good example with what to do with negative exponents here, you can still just apply the quotient rule from the get-go. This is 10 to the 4, and you would subtract the negative power because we're subtracting because it's the quotient rule, right? This is the quotient rule. This is from the negative power in the denominator. So it actually becomes 10 to the 4 plus 7, realizing that those 3 10s will move up to the top, not 7, excuse me. It will be 7 when we're done. I'm jumping the gun here. 4 plus 3, and that will be 10 to the 7. And I would just go ahead and leave that as is. All right, and your very last one here, this is a really good one again to take care of that negative exponent on the outside first by flipping that inside fraction. So I'm going to move 7z cubed to the top, and I'm going to move 4x squared to the bottom to make that outside power positive. This then becomes 7 squared, z cubed gets squared, over 4 squared, and x squared gets squared. So your final answer here would be 49 when you take 7 squared, z to the 6th over 16 from 4 squared x to the 4th from taking 2 times 2. This is another example where if you would have had anything like if the z was actually an x from the beginning, you could have simplified inside the parentheses first and then distributed that outside power, which again is something I would always suggest doing. You guys are gonna get a lot of practice with this on the homework. I'm gonna have a big packet of problems for you guys to practice with solutions ready to go so you know you're doing them right as you go. I've seen with exponents, it really just takes seeing, there's so many different ways, so many different problems, so many different setups that are all just handled a little bit differently. You just need a lot of practice with those to understand. Now, we've really just been kind of going through the rules, right? Hammering these out. And I just want to show you some examples of when these rules become very helpful. So what happens a lot of the time is numbers get way too big when we're doing exponential rules with them. And the calculator won't even actually do the work for us if it's too big. So a lot of the time what we'll have to do is actually apply these exponential rules before the calculator will handle the work. So that's just kind of what I want to look at here. Where are some really big numbers that we might be dealing with where we need to take them to exponents, and how could we simplify that a little bit before we even think about plugging it into the calculator? So here is an example. We're talking about Jupiter, the largest of the planets in our solar system, which is approximately 7.14 times 10 to the kilometers, just the radius of Jupiter. That's how big it is, okay? Very roughly, okay? But that's pretty close. Now, we're going to assume, and we know planets aren't exactly spherical, but for the sake of this problem, we're going to assume it's roughly spherical so that we can actually estimate the surface area of Jupiter by using the surface area of a sphere formula, which is 4 pi r squared. So you'll notice here, what we have to do is square that radius that is in an exponential or scientific notation because it's such a large number. So how can we help simplify this? So here we want to find the surface area. So we want to take 4 pi r squared, which means we have 4 pi times 7.14. Oops, let's see if I can get that to look a little nicer. 7.14 times 10 to the 4th, and that's what needs to get squared. So you're looking at a product of two different bases with this scientific notation number, so each one of those bases needs to get squared. So we can start simplifying this before we plug it into our calculator. We say, oh, that's 4 pi times 7.14 squared. The 7.14 gets squared and the 10 to the 4th gets squared. So essentially what we're doing is saying, okay, here's all of our smaller numbers, and then when we put all those zeros together at the end, that would be times 10 to the 4th, which gets squared, so 10 to the 8th. And now this is just a small number we can plug in, a small calculation we can plug into our calculator and know that it's times 10 to the 8th at the end. So if you take in your calculator 4 pi times 7.14 squared, I'm going to go ahead and do that again. You should get about 641. You're gonna have to round because it's going to be a number that goes on forever. Yep, so I'm just going to go ahead and round to, and if you use 3.14, you get about 640 instead. So, yeah, that'll be about 640. We'll go ahead and round to the nearest whole number. So 640 times 10 to the 8th. And then again, just this is good review of scientific notation. Just make sure that your final answer there is in correct scientific notation. So 640 is not a number between 1 and 10. We would need that to be 6.4 to be a number between 1 and 10, which means that normally when we were about to take 6.4 times 10 to the 8th, we would have moved the decimal point out 8 more times. Now we need to move it 2 more times. Another way you can see this now is, oh, I had, and let me get rid of that decimal because it was not 6.4 from the beginning. Our original problem was 640 times 10 to the 8th. 6.4 then would be 640 by taking it times 10 twice, right, to get back to 640. If I have the decimal point here, I have moved it twice. Then that's 640, and that needs to get multiplied by 10 to the 8th, and we can simplify this using those exponential rules. I have 10 squared times 10 to the 8th. That means I add the powers, and that would be times 10 to the 10th. Another way now that we can simplify those scientific notation terms, where sometimes it's hard, where you don't know if you're going to add or subtract those two 10s from that original 8. And that's a 0 there, not an 8, 10 to the 10th. Okay, and in this particular case, we took kilometers and squared it. We have surface area, so we have kilometers squared. So see if you can't do that to estimate the volume of Jupiter using the volume formula for a sphere. You should again have 4/3 pi times that 7.14 times 10 to the 4th, and this time it's going to get cubed. So our number we can plug in the calculator is 4/3 pi times 7.14 cubed, and then again we summarize all those zeros all together in that last power there. So this will be about, when you plug it into your calculator, rounding to the nearest whole number, 1,525 times 10 to the 12th. And then again, you can think, okay, my decimal point should be at 1.525. That means it moved 1, 2, 3 times, and 1.525 needs to get multiplied by 10 3 times to become a bigger number. That then has multiplied by 10 12 times on the outside. So my final answer here would be 1.525 times 10 to the 15th power. You will add the powers when they're being multiplied. We took kilometers here and cubed it, so the volume would be that many kilometers cubed, a huge number, as we would expect with the fact that we're trying to estimate the volume of a planet. Now this next one works out really well. This is one of my favorite problems. Okay, so you see these really big numbers from the beginning. The area of Alaska is approximately 3.6 times 10 to the 8th acres. The state was purchased from Russia in 1867 for $7.2 million. And we want to find the price per acre, and I want you to do this without a calculator, only using those exponential rules. So price per acre means I need to take the price, which is 7.2 million, so that's times 10 to the 6th, that million there, over price per acre, so price divided by acre, 3.6 times 10 to the 8th. And now again, we can handle the numbers separately from the exponential terms since everything's being multiplied. 7.2 divided by 3.6 is just 2. And if I need to take 10 to the 6th divided by 10 to the 8th, that's just 10 to the 6th minus 8. So this whole thing is 2 times 10 to the negative 2. And since we're talking about price per acre, it would be helpful to know what that number is in decimal form. So go ahead, this is a good practice of 4.1. What would that number be in decimal form? And you should get 0.02. Remember your units here. That was dollars per acre. So when we bought Alaska, it only cost us about 2 cents per acre. And we did that calculation with giant numbers in just a couple of seconds by using some of those exponential rules. All right, guys, you're gonna have a lot of good practice with this in the homework. I'll have that posted in Talon. And just again, as always, shoot me questions when you have them.